23, we study power series expansion of e to the I theta. This one is known to be cosine theta plus I sine theta. This expression is called Euler's formula. Euler is a very important figure in physics as well as in mathematics. He was a genius, and he was very lucky because he was born after Newton. And about 50 years late after the publication of Principia by Newton, Euler extended Newtonian mechanics from point particle to system of particles. Sure, the solving the planetary motion by Newton was for many-body theory, but this is a two-body system, sun and a planet. But Euler constructed the theory that is applicable to the rigid body, for example, spinning top. He introduced the notation pi, and this I is a square root of -1. These are due to Euler, and he also uses E for the Euler's number, although it was first introduced by Bernoulli. Anyway, the exponential function, especially extended to the complex plane, is a very, very useful formula in physics, mathematics, and many places. So we study this today. We know exponential function has the derivative that is itself. And we'd like to find the derivative of exponential I theta. This can be obtained by chain rule. Let's see. Here, we just replace theta with I theta. Then we would get e to the I theta d I theta equals e to the I theta. And I can pull this I out because it's a constant, and then multiply both sides with I, then I would get this differential equation. So derivative of e to the I theta must be the same as e to the I theta, except that I is multiplied. Therefore, it is apparent that the solution of this differential equation is this up to over constant, because I can multiply any constant both sides. So if g theta is a solution, c times g theta is also solution. In addition, because we have only a single derivative, after the integration, you can do it by integration by separating variables like that. And then you'll find log, and this part is a theta. Anyway, there should be only a single undetermined parameter that is integral constant, integration constant. So evidently, the general solution of this differential equation is something multiplied by e to the I theta, nothing else. And if I require an initial condition such that if I substitute theta equals 0, it gives 1, then this over constant, this integration constant is determined as 1. So this is the answer. Solve the following differential equation with the Frobenius method. We learned that if we find the solution of a differential equation is regular, that means it has no divergence in it, in which we are interested in, then we can always make a series expansion that is equivalent to the Taylor series expansion. And we find we have initial condition that at z equals 0, it is 1. So we can think that it can be expanded in the power series in this variable theta. For example, there should not be something like this. They are divergent as theta goes to 0. So these kind of terms are absent. Therefore, it should be 1, theta, theta squared, and so on. Their linear combinations should be the answer. Okay. So if I substitute this initial condition, theta equals 0, every term vanishes except for the initial term at k equals 0. So I can determine the initial condition for determine the initial entry of this sequence CK. Okay, so I'd like to convert this. It is 1 plus sigma k runs from 1 to infinity ck theta k and z theta. So I'd like to substitute this one into this differential equation. First of all, the first order derivative removes this constant term, and this part will become, we have, this is starting from 0. As soon as you take the derivative, this k initial value, k equals 0, is being removed. What about the right-hand side? If I substitute this in here, it is still the same. Okay, here I have a power theta to the k minus 1 on the left side, and on the right side we have a theta to the k. So I'd like to compare this with the same power, so we need to reorganize the summation. Remember, this k is a dummy index that can be replaced with anything else, as long as the result is the same. First of all, substitute k equals 0. I don't need this, so we begin with the k equals 1. And then my main goal is to replace this 1 into k. That is to add every k by plus 1. So if I add any k by plus 1, it becomes k, it becomes a k plus 1, it becomes k plus 1, and then what happens? This 1 should be 0. So if I substitute, so first I substitute k plus 1 for the original k, it becomes k plus 1, k plus 1, k. And then initial value of this was k equals 1. What is the initial value of this factor? If I substitute 0, it is 1. Okay, so these two are equivalent. So this series expansion should be the same. By the way, we know 1 theta, theta squared, theta cube, everything, they are all linearly independent. Okay? Therefore, if I have a two convergent power series, as long as they converge to a certain value, then the coefficient should be uniquely defined. Okay, that's the reason why we always prefer to use linearly independent basis for the description of a vector in a Euclidean space and this kind of functional space. So if I compare these two coefficients, ck plus 1 is completely determined by ck and additional factor. I have divided this one, and we have I in here. C0 was already determined by making use of the initial value. We keep using this recursive relation to find that this is the initial value. Substitute a 0 in here, then you will find 1 in the denominator and I. 2, to get C2, I substitute k equals 1, so it becomes 2, and so on. So I have increasing power of I, and I have increasing factor of n, 1, 2, 3, 4. Therefore, finally, I can determine the coefficients as if I have even terms, it strips by twice, so I squared is minus 1. So we have minus 1 to the k factor. Because we have a k factorial style denominator, if I have even number, then the denominator becomes even factorial. The same is true for the increasing power of I, and I have increasing oscillating factor, and in the denominator, if it is an odd number, it is like that. And the initial condition is coming from this. I have I, if I substitute k equals 0. As a result, I can separate the even part and odd part separately. And even part has this kind of summation. And odd part always has a pure imaginary number. That is this. And we find that these real part and imaginary part are completely determined by cosine and sine. So we have finished our proof for the Euler's formula using the Frobenius method. We could have substituted cosine and sine into the differential equation. So it is also true, because you know the derivative of cosine is minus sine and derivative of sine is cosine.